Hey everyone, very excited to be here. My name is Supriya, and I'm an engineering manager at Meta working on PyTorch. In today's talk, I'll be going over some background about PyTorch, highlight some newly added features, and then conclude with how you can accelerate generative AI models using native PyTorch code. So here's a high-level agenda of what we'll be going over today. I'll first talk about some background and metrics about PyTorch, and then do a bit of a deep dive into some of the newly added features in PyTorch 2.1. I'll then switch gears and talk about how you can accelerate some significant generative AI models using native PyTorch code, and then share model results for these models. With that, let's get started. Cool. So what is PyTorch? PyTorch started about 7 years ago with the goal of powering researchers. Today, it's one of the leading AI frameworks powering a diverse set of use cases, from self-driving cars to perhaps the robot vacuum that might be running in your living room. It's open source, it's a community-based deep learning platform, and if you haven't, then you should definitely check it out today. So as I mentioned, here are some metrics about PyTorch. These are some numbers that speak for the growth in PyTorch over the past few years. The chart on the left goes over the growth in researcher usage over the past few years. There are close to 7,000 GitHub repos that are using PyTorch and are associated with AI research papers this year. 60% of AI research implementations have chosen PyTorch as compared to other deep learning frameworks. The graph on the right talks about the number of open source repositories that use PyTorch today in GitHub. There are over 600,000 repositories on GitHub that are using PyTorch. And we've observed over 20% year-over-year growth in new repositories using PyTorch. PyTorch has also made a significant impact on the tech industry. Data from LinkedIn suggests that there are over 65,000 LinkedIn professionals that have PyTorch listed on their profile. There are also 3,000 jobs associated with PyTorch, and we have observed over 50% increase in PyTorch professionals just this year. So let's recap a little bit to the last version of PyTorch. PyTorch 2.0 was released earlier this year. It saw over 20 million downloads across different platforms. So yes, it was a pretty significant release for us. It also added a bunch of new features, most notable of which is Torch Compile, which significantly sped up training and inference of a large variety of models while offering the same eager mode development experience. So let's flash forward to the next release, which is also what this talk is mostly going to be about, PyTorch 2.1. This was released earlier this year on October 4th, and we also presented a lot of features that we released in PyTorch 2.1 at the PyTorch conference, which happened in October this year. Going back to the numbers, we saw close to 7,000 commits and 784 contributors that contributed to PyTorch since 2.0. So let's dive into some of the features that PyTorch 2.1 has to offer. Note that this is by no means the exhaustive list of everything we've introduced in 2.1. For the full list, you should definitely check out our release notes. So as I mentioned before, Torch Compile was a pretty significant feature for us, and we are constantly making improvements to it. So first, I'd like to go over some improvements that we've made to Torch Compile since the 2.0 release. First is the automatic dynamic shape support. Deep learning compilers commonly only work for static shapes. That is to say, they produce compile programs which work for a specific configuration of input shapes, and if you recompile, and you need to recompile if any of the input shape changes. With dynamic shape support, it allows Torch Compile to generate a single kernel that can work for many sizes at only a modest cost to efficiency. Dynamic shape has been greatly stabilized in PyTorch 2.1 and is now automatically enabled if Torch Compile notices a recompilation due to varying input shapes. The next, we've added support to how to compile NumPy operations in Torch Compile itself. So Torch Compile understands how to compile NumPy operations by translating them into PyTorch equivalent operations. Because this integration operates in a device-agnostic manner, you can now GPU accelerate your NumPy programs and get the wins for free. Torch compile also works well with autograd.function now. It has improved composability with autograd.function, and we can now trace and optimize the backward function of user-defined autograd functions, which unlocks training optimizations for models that make heavier use of extension mechanisms. So the next feature I want to touch upon is something we newly introduced in 2.1. It's called torch.export. So torch export provides a sound tracing mechanism to capture a full graph from a PyTorch program based on new technologies provided in PyTorch 2.0. This can be intended to run on different environments, which can also be Python-less. How torch export does this is that it extracts a single graph representation from PyTorch programs by tracing the target function given some example inputs. So you might ask, how is this different from the previous version of TorchFX symbolic trace? Well, it captures a much higher percentage of models compared to FX. On 14,000 GitHub models, we see over 88% pass rate on models that are exported via torch export. One of the advantages of exporting a model is that you get an IR where users can run custom graph transformations on. For example, quantization, which I'll be talking about a little bit in a bit more detail in the next few slides. The export IR can also be serialized, saved, and transferred and loaded back for execution with or without Python. So here's a small code snippet walking through how you can use the export API. In this example, I have a simple model, in this case, it's just a small module. You instantiate the module, and you call export on the module with sample inputs. This generates the exported program, and if you print the type, you can verify that it's of type exported program, and you can further perform other optimizations or graph transformation on this exported program. As I mentioned before, one advantage of exporting the model is that you can perform various graph transformations on the IR. One such transformation is quantization. What is quantization? Quantization refers to techniques for performing computations and storing tensors at lower bit widths than the floating point precision. For example, int 8, int 16, or int 4. In PyTorch 2.1, we added support for both post-training quantization and quantization-aware training on models that are exported via torch.export. Users can use a backend-specific quantizer object to enable lowering a single PyTorch quantized program to different backends. These could be backends on server CPU or different edge backends like your mobile phones or specific DSPs. Backend developers can write their own quantizers and expose methods that allow users to express how they want to quantize their model. This is done via a programmable API for both backend developers as well as users, so it's totally configurable. We also offer the option to specify quantized computation using integer arithmetic in the PyTorch model itself. By doing this, you can achieve higher numerical precision on the server and be able to debug your model numerics more accurately. So here I'll just go through a short example of showing how you can use these new APIs. There are two high-level steps. The first step is capturing the program or exporting. Here we call the capture pre-autograd graph, which is in this case equivalent to torch export. And the next step, we perform quantization. So the user would first have to call a specific quantizer. In this example, we are calling an XNNPACK quantizer, which is the quantizer optimized to run on the XNNPACK backend, which is meant for CPU. Once this quantizer is instantiated with a config or like a quantization config, you call the prepare function. What the prepare function does is it takes the model and the quantizer and it inserts observers into the model so that you can collect statistics that are necessary to quantize the model. As a next step, you can either calibrate the model for post-training quantization or train the model for quantization-aware training and generate those statistics that are required to quantize it. The final step, you would convert the model, and the convert step produced a final quantized model, which is optimized to run on the target backend, in this case, the XNNPACK backend. The next feature I'd like to highlight is 2.4 semi-structured sparsity. Torch.sparse now supports creating and accelerating compute over semi-structured sparse tensors. Semi-structured sparsity is a data layout that was first introduced in NVIDIA's Ampere architecture. We've added support in 2.1 for creating the 2-4 semi-structured sparse tensors using a one-line API. This supports accelerated inference via both Cutlass kernels and QSparseLT by running faster sparse matmulls during inference. QSparseLT is a library that's provided by NVIDIA for running 2-4 sparse matmulls. By compressing the tensors to this format, you can achieve a compression ratio of 56.25 for float 16 and 62.5% for int 8. So here's a code snippet on how you can use this API. You first have like your input tensor here, which is x, and then you instantiate a mask. This is just for illustration purposes. You can use different pruning algorithms to determine how you calculate this mask. The mask here is essentially setting 2 out of 4 values to 0, which is the format expected by the sparse kernel. Then you call the linear layer, and you set the weight of the linear layer to the masked value. And you call the toSparse semi-structured API, which in this case is what is responsible for compressing it to run accelerated inference. When you then call the linear operator with a sample input, it will automatically take advantage of the fast kernels during inference. So I now want to shift gears a little bit and talk about how you can accelerate generative AI models using pure PyTorch code. So the space of generative AI is rapidly evolving. As you can see, many innovative models have released in just the last couple of years, each of them pushing the state of the art of what's possible in this domain. And as with any new model released, the community wants a way to be able to run it efficiently on different hardware. The generative AI landscape is no different. From llama.cpp to frameworks like Mosaic ML or XLlama, we have many different options of frameworks that have been built to run these models faster during inference. But can we do this with native PyTorch without having to rely on the external frameworks? So I'd now like to walk through some techniques that you can use in PyTorch to accelerate these models. The first such technique I want to talk about is SDPA, or scale dot product attention. PyTorch now includes high-performance implementation of the transformer API using a custom kernel architecture for scale dot product attention. And transformer APIs are at the heart of most generative AI models today. We have multiple SDPA custom kernels which are supported, with a kernel selection logic that will pick the highest performance kernel for a given model and hardware type. Some of the options of kernels that we've integrated include the flash attention kernel and the Xformers memory efficient attention kernel. We also added the flash attention v2 kernel, which was released earlier this year, and it's now available in PyTorch 2.1 and is expected to be 2 times faster than the previous SDPA implementation of flash attention. I will share some results later on how this technique helped with the performance of the segment anything model on GPU. So here's how you can use the SDPA kernels. You simply have to call the functional operator scale dot product attention with the sample inputs. So in your model, you can find where the transformer implementation exists, and if you go and make the simple one-line change, you can take advantage of the accelerated kernels that PyTorch has to offer. The next technique I want to talk a little bit about is nested tensors. Firstly, what is a nested tensor? In a regular tensor, each dimension has a fixed size. Nested tensors are similar to regular tensors, except for their shape, where not all dimensions have regular sizes. Some of them are jagged. Nested tensors are a natural solution for representing sequential data within various domains, like in NLP, where sentences can have variable lengths, so a batch of sentences forms a nested tensor. Or in computer vision, where images can have variable shapes, so a batch of images forms a nested tensor. This is pretty common in a lot of transformer-based models, or also common for models where you have varying input-output shapes, where you run batched inference over images. By simply batching the images instead of running them serially using nested tensors, we are able to observe close to 2.8x speedup on the segment anything model. So this is how the nested tensor API looks like. You have two torch tensors here, each of different shape, A and B. And then you invoke the nested tensor API with the two tensors as inputs, which then generates a new tensor object called nested tensors, which includes these two tensors as inputs. So in your model, if you have inputs with varying shapes, you could potentially use a nested tensor and take advantage of the batched processing. So I touched upon quantization a little bit. We also added support to do quantization on the GPU, which is pretty relevant for generative AI models today. To recap, quantization trades off numerical precision for reduced model size and increased execution speed. Some of the benefits of using int8 math over FP32 means that we can reduce the model size by 4 times on disk and in memory. And the matrix multiplication also requires lesser computation. And we've seen theoretical speedups of up to 16x compared to FP32. So what are some of the techniques that you can use to quantize models on GPU? You have dynamic int8 quantization. This is dynamic because the activations are quantized dynamically during inference, while the weights are quantized ahead of time. You have static int8 quantization, where both the activations and the weights are quantized ahead of time. And then you have weight-only quantization, which, as the name suggests, just runs the weights in a compressed format, but stores the activations in full precision. We implemented both dynamic and weight-only quantization for GPUs, and we see good results on both segment anything and Llama 2 model, as you can see below. So on the SAM VITH backbone, int8 dynamic quant leads to about 9% speedup, and on the Llama 2 7 billion model, which is pretty memory bound, int8 weight-only quantization leads to about 47% speedup. So we have an API available that you can try out for doing this on your model. It's available in PyTorch labs under the AO repository. Here's a sample code of how you could use it. You have any user model. In this example, it's a sequential module with a single linear layer. You have sample inputs. And then you call this one-line API depending on what you wish to do. If you wish to apply weight-only quantization, you can call apply weight-only int8 quant on the model. And if you wish to apply dynamic quantization, you can call the apply dynamic quantization API on the model. You can also torch compile the model to improve performance further. And these APIs compose well with torch compile. And then once you run the model, you can take advantage of the accelerated int8 kernels during inference time. I want to talk a little bit more about two-for sparsity and how we added support for that on GPU. As we spoke before, people want faster matrix multiplication. And that's one of the most compute-intensive operators for most generative AI models. And enabling two-for structured sparse weights gets us that. Introducing two-for sparsity can come with some accuracy impact. And in order to elevate that, you can fine-tune your sparse neural networks to reduce the accuracy impact. And to do this, you can leverage the Torch AO pruning APIs and use different algorithms to prune the weights. This also composes well with int8 quantization. So you can have 2-4 sparse int8 kernels, which will give you 62.5 compression ratio for weights and up to 4 times theoretical speedup compared to dense FP16. So let me walk through the code a little bit here. It's a bit more involved, so bear with me. I'll go step by step. I'll first talk through the helper functions that you can use to sparsify or prune your model. In this case, we will use the torch.ao.pruning package, which contains a weight norm sparsifier, which is a magnitude-based sparsifier. These sparsifiers work by applying mask parameterizations to the weight tensors in the model. This lets them simulate sparsity by masking out the prune weights. We also have to decide what layers of the model to apply sparsity to, in this case, we apply it to all the linear layers, and we set that in the sparse config. We now go to the sparsifier.prepare, and the prepare step inserts the parameterizations necessary to mask the weights of the model. The step function is used to update the mask based on the logic specified in the pruner. In this case, it will update the mask based on the magnitude of the weights. When we reach a final satisfied stage, we can call the squash mask function, which is used to fuse the weight and the mask together. So the final result in this example would be that you have a weight tensor which is compliant with the 2.4 sparse format and has been pruned using the weight norm sparsifier. Once we have the model in this format, we can accelerate for inference using the one-line API that I mentioned before, 2-sparse semi-structured. We update the weight of all the linear layers in the model to use this format, and once we run the model during inference, it will automatically run the sparse kernels during runtime. The next technique I'd like to talk about is pretty relevant these days in the context of running large language models, which is 4-bit quantization. Quantizing the weights down to 4 bits can have an impact on model accuracy, and GPTQ is a technique to reduce that. So GPTQ is a one-shot weight quantization method, which is based on approximate second-order information of the weights. We leverage torch.export to prototype an easy-to-use GPTQ implementation that you can try out today. However, to run this efficiently on GPU, we do need some custom 4-bit quantized matrix multiplication, which we have implemented in CUDA. So here's the example API that we used to implement this. You have a 4-bit GPTQ handler. This handler is responsible for converting the weights to 4 bits and running the model as well. So as a first step, you create the quantized state dict. You can run this step ahead of time so that your weights are already in the 4-bit format, and you can store the weights separately. In the next step, you can prepare your model for runtime. So here you would do 2 steps where you first ready the model for runtime here, which is done by the convert for runtime function, and then you can load the previously saved state dict by calling the load state dict function. So as an end result, you have a model that has been 4-bit quantized. Great. So now I spoke about a few different techniques. Let's talk about some of the results that we observed on models using these techniques. So I'll mainly go over 2 models here, the segment anything model and Llama 2. Segment anything, or SAM, is a zero-shot vision model for generating promptable image masks. Our SAM baseline is Facebook Research's unmodified model using a floating point 32 data type and a batch size of 1. And here we show the benchmark results on the VIT-H backbone. So on the graph on the left, you can see the improvement in the performance or the images per second for the segment anything model. We start with the floating point 32 model, and as a first step, we convert it to run in 16-bit precision. This itself gives us a big boost. Torch compile further improves the performance. And once we introduce SDPA, or PyTorch's native scale dot product attention kernel, we can significantly increase the batch size. You can see that the batch size here has gone up from 16 to 32, so you can run the model faster. And for the following techniques, we continue measuring with a batch size of 32. We tested with a custom Triton implementation that further improves the performance of SDPA. We added nested tensors, and then we added int8 quantization and sparsity. Overall, we have achieved over 8x speedup over the FP32 ego baseline. And we also observe no accuracy impact when we run the model with int8. We do see some accuracy impact with 2.4 sparsity, mainly because we did not apply fine-tuning to reduce or to prune the model in this case. The graph on the right shows the memory utilization at batch size 32. So as you can see, we start with a batch size of 1, and once we reach SDPA, we can increase the batch size to 32. And all the further techniques reduce the batch size quite significantly to make the memory utilization similar to what we observed of floating point 16. So I'll now talk about some results on the Llama 2 model. So the main techniques we applied on the Llama 2 7B model was torch compile, int8 weight-only quantization, and 4-bit GPTQ. By applying these techniques, we saw over 7.5x speed up over the FP16 eager baseline. You might wonder what's the accuracy impact on the Llama 2 model by applying some of these quantization techniques. Well, there is minimal impact when we apply 8-bit quantization, as you can see on some of the metrics in the chart on the right. And with 4 bits as well, we don't see significant degradation because GPTQ helps us recover some of that. So if you look at the metrics, 4 bits and 8 bits perform quite similarly in terms of model accuracy, with 4 bits giving a pretty significant boost in performance. We also applied some other techniques on Llama 2, including speculative decoding and tensor parallelism. By applying these, you can see that the final bar here goes up to close to 244 tokens per second on the Llama 2 7B model. We believe that this is the current state-of-the-art performance for Llama 2 on GPUs. We also apply the similar techniques on Llama 70B, and by applying them, we achieve close to 80 tokens per second on an A100 GPU. Note that without applying these techniques, the Llama 2 70B model would on an A100 GPU because of the memory restrictions. So if you're interested in checking out these models or trying some of these techniques, you can check out these following repositories on PyTorch Labs. We have one for segment anything fast, and we also have the AO repository, which includes the GPU quantization techniques I talked about earlier. And we are very soon going to release the Llama 2 repository as well, called GPT-Fast. With that, that's all I had. Thank you for listening to the talk. Please check out the other resources on PyTorch. And I have a few more minutes, I think, for questions in case people would like to ask some right now.
So I have a quick question about like this Facebook Meta is planning in the future like turn PyTorch into a hardware agnostic framework, or at this point you still needed to do all the quantization and all of this kind of stuff for hardware specific?
So by hardware agnostic, do you mean just?
So pretty much if I train my model or I build my model using PyTorch, at this point I should be able to run the model in different hardware targets, or?
So what kind of hardwares are you talking
I'm
about?
talking more about the accelerators, you know, like
About, sorry?
accelerators, the
Accelerators.
GPU, like XLA and all of this kind of stuff is.
Right. So with the quantization, the export-based quantization that I talked about earlier, once you run the convert step, you technically get a backend agnostic representation, but you can further run like custom graph optimizations to map those operators into your custom like hardware accelerator operators. So in terms of quantization, you would maybe get a pattern like dequantize, floating point operator followed by quantize, and you would map that pattern to your custom hardware quantized operator. So you can further run lowering passes on the reference quantized model generated to make it work for your hardware. The reason why we have a backend specific quantizer is to help with accuracy, because different hardwares may have different requirements or specifications on what numerics they can run or what operators they support. So we have the ability to specify that ahead of time so that the model not just like is able to lower but also performs better. But if you do not really care that much about accuracy, you want something that runs across different platforms, then you can still use the same flow and lower it on different hardwares using your own custom lowering stack.
Cool. And finally, the other question that I have is PyTorch is doing a really good job with the building blocks for the modeling part, but so what about the deployment part? So do you guys, like you have PyTorch is thinking about having an API to deploy models in mobile devices or IoT systems or this kind of stuff?
So it's actually a little hard for me to hear the question.
My question is about that PyTorch is doing a really good job with the building blocks for modeling, but so what about the deployment? So at this point, is there any API to deploy your model in a mobile device? Or?
Right. No? So one major release we had recently, which I did not cover here, was Executorch, which PyTorch released in the conference earlier this year, which is the ability to take any PyTorch program and deploy it on multiple different mobile backends. ranging from like ARM to Apple to Qualcomm. And we are also actively engaging with these different vendors. And Executorch is also open source, so you can check that out as well. Cool. All right. Thanks for your time, everybody. It was great presenting. Thanks.